Time is not constant. Space breaks reality. The universe doesn't work the way you think. And now, the most powerful telescope ever built has proven it. Welcome to the universe. Science Nucleus, exploring the core of reality. For decades, cosmologists believed they understood the story of the universe. The Big Bang, expansion, galaxies forming over billions of years, a clean, predictable timeline. But the James Webb Space Telescope has shattered that timeline. And what it found is not a small correction, it is a structural crisis. In this video, 3 questions. Why did JWST find galaxies that formed before time allowed? Why is the universe expanding at 2 different speeds? And why are the fundamental constants of reality so precise that even a fraction of change would erase existence itself? The Lambda CDM model, the standard model of cosmology, it is the backbone of everything we think we know about the universe. Lambda, dark energy, the cosmological constant, accelerating the expansion of space. CDM, cold dark matter, the invisible scaffold holding galaxies together. Together, Lambda CDM predicts a clear sequence. The Big Bang creates a hot, dense plasma. The universe expands and cools. Dark matter collapses into halos. Gas falls into those halos. The first stars ignite around 200 million years after the Big Bang, and galaxies assemble, slowly over billions of years. This model works. It predicts the cosmic microwave background with extraordinary precision. It explains the distribution of galaxies across the observable universe. It matches supernova data. It is, by any standard, a scientific triumph. But then the James Webb Space Telescope opened its eyes, and the Lambda CDM model began to crack. JWST is not an incremental upgrade. It is a revolution. Its primary mirror is 6.5 meters across, nearly 3 times the diameter of Hubble. It operates in infrared, and it sits at the L2 Lagrange point, 1.5 million kilometers from Earth, shielded from the sun by a tennis court-sized sun shield. This is not just a bigger telescope. This is a time machine, because light takes time to travel, and JWST can see light that left its source over 13 billion years ago. In July 2022, JWST delivered its first deep field image, and cosmologists stared at their screens in disbelief, because there, in the infrared, sat galaxies that should not exist. The JADE survey, the JWST Advanced Deep Extragalactic Survey, identified galaxies at redshifts greater than 10. JADES-GS-Z 13-0, redshift 13.09. Light emitted when the universe was only 300 million years old, and yet a galaxy with stellar mass, with structure, with stars already ancient within it. Then came JADES-GS-Z 14-0, redshift 14.17, the current record holder. Light from when the universe was only 290 million years old. And this galaxy contains not just stars, but dust. Dust requires multiple generations of stars to form. Stars that live, explode, and seed the cosmos with heavy elements. Do you know what redshift actually measures? Redshift measures how much the universe has stretched the light traveling through it. A photon leaves a galaxy 13 billion years ago. The universe expands during its journey. The photon's wavelength stretches. It shifts toward the red end of the spectrum. The more the universe has expanded since the photon was emitted, the higher the redshift. Redshift is not a speed, it is a record of cosmic time. When JWST detects E greater than 14, It is looking at light that was emitted before the universe had enough time to build what JWST is seeing. This is not a calibration issue. This is not an observational artifact. This is a crisis. The SEERS survey confirmed the problem. SEERS-93316, a galaxy candidate at Redshift 16.7. If confirmed, it existed when the universe was only 230 million years old. That is roughly 1.7% of the current age of the cosmos. And then there are the massive galaxies. Not just early, but enormous. In February 2023, a team led by Ivo Labbé reported galaxies at redshifts between 7 and 9 with stellar masses up to 10 billion solar masses. That is the size of the Milky Way, formed in under 1 billion years. The Lambda CDM model does not forbid early galaxies, but it requires them to be small, dim, slowly assembling. JWST is finding them large, bright, already mature. The model does not predict this. Not at this pace, not at this scale. What does this mean? 3 possibilities. 1. The Lambda CDM model is incomplete. Perhaps dark matter behaves differently in the early universe. Perhaps dark energy was stronger. Perhaps we are missing a fundamental force or particle that accelerated early galaxy formation. 2. Star formation in the early universe was dramatically more efficient than any current theory allows. Population 3 stars, the hypothetical first generation of stars, may have been hundreds of times more massive than the Sun. Burning hot, burning fast, creating galaxies and cosmic heartbeats. 3. The galaxies are not what they appear to be. Some may be active galactic nuclei, supermassive black holes accreting gas at extreme rates, producing infrared light that mimics stellar emission. Bright, but not as massive as they seem. This would reduce the problem. It would not eliminate it. None of these possibilities is comfortable. Each one demands that we rewrite part of the standard model, and the data keeps coming. JWST has not stopped observing. Every new deep field deepens the crisis, but the galaxies are only the first crack. There is another, and this one strikes at the most measured number in modern cosmology. What happens when 2 of the most precise measurements in physics give 2 completely different answers? Not approximately different, not slightly different, 7 standard deviations different. The Hubble constant, symbol H0, it measures how fast the universe is expanding right now. Not in the past, not in the future. Now. It is expressed in kilometers per second per megaparsec, and it is the single most important number in cosmology because every calculation about the age, size, and fate of the universe depends on it. In 1929, Edwin Hubble observed that distant galaxies were moving away from us. The farther the galaxy, the faster it receded. This was the first direct evidence that the universe was expanding, and the rate of that expansion became the Hubble constant. For nearly a century, cosmologists have been trying to measure H0 with ever greater precision. And for nearly a century, the measurements have been converging, or so it seemed, until they split. Method 1, the cosmic distance ladder, also called the late universe approach. It measures H0 by working outward from the nearby cosmos. First, parallax measurements of nearby stars. Then, Cepheid variable stars, whose pulsation period directly reveals their true brightness. Then, type 1a supernovae, standard candles visible to the naked eye, a supernovae. Standard candles visible across billions of light years. Step by step, rung by rung, astronomers climb outward, and at the top of the ladder they measure H0 directly. The SH0ES project, led by Adam Rees, has refined this measurement over 2 decades. Their result, 73.04 kilometers per second per megaparsec, with a margin of error of just 1.04. That number is not a guess. It is built on thousands of observations. It is, by any reasonable standard, one of the most precise measurements in all of astrophysics. Method 2, the cosmic microwave background. The afterglow of the Big Bang, the oldest light in the universe, emitted when the cosmos was only 380,000 years old. The Planck satellite mapped this radiation across the entire sky with extraordinary precision. From the CMB, cosmologists do not measure H0 directly. They measure the acoustic peaks, the fingerprint of sound waves propagating through the primordial plasma. Then they plug these measurements into the Lambda CDM model and calculate what H0 must be for the early universe to evolve into what we observe today. The Planck result, 67.4 kilometers per second per megaparsec. 2 methods, 2 results, 73.04 versus 67.4. A difference of 5.6 kilometers per second per megaparsec. That might sound small, it is not. But what if neither side is wrong? In particle physics, 5 sigma is the threshold for a discovery. The Higgs boson was confirmed at 5 sigma. The Hubble tension has reached 7 sigma. Let that settle. The gap between these 2 measurements is more statistically significant than the detection of the Higgs boson. This is not a measurement error. Both methods have been checked, rechecked, cross-checked, and challenged by independent teams. Neither has cracked. The tension is real. So what are the proposed solutions? 1. Early dark energy. A burst of additional dark energy in the first 100,000 years after the Big Bang that accelerated expansion temporarily, then faded. This would change the CMB calculation and potentially reconcile the 2 values. 2. Modified gravity. Perhaps general relativity breaks down on the largest scales. Perhaps gravity behaves slightly differently across cosmic distances, and our equations need correction. This would be revolutionary and deeply destabilizing. 3. New particles or interactions. A sterile neutrino, a decaying dark matter component, a previously unknown force that altered the expansion rate in the early universe. Each possibility opens a new chapter in physics and closes none of the existing ones. 4. Systematic error still hiding somewhere. This is the least exciting possibility and the most humbling. Perhaps there is an unrecognized bias in one of the methods. A calibration error, a selection effect. No physicist wants this to be the answer, but honesty requires keeping it on the table. The Hubble tension has persisted for nearly a decade. It has survived every attempt to resolve it. New data from JWST has only confirmed the distance ladder result. New CMB observations have only confirmed the Planck result. The gap is not closing, it is widening. And this is where the 2 crises begin to converge. Because if the Lambda CDM model is wrong about galaxy formation and wrong about the expansion rate, then the model is not merely incomplete, it is fundamentally broken. But there is one more crack, and it may be the deepest of all. Not a measurement that conflicts with a model, but a fact of nature that conflicts with probability itself. What if the universe is not just unexplained, but impossibly precise? What if the very laws that govern reality are tuned within margins so narrow that even the slightest deviation would make existence impossible? The fine-tuning problem. It is not theology, it is not philosophy. It is a mathematical fact about the structure of physical law. And it is, by any measure, the most unsettling observation in all of science. There are 6 fundamental constants that define whether the universe can contain matter, chemistry, stars, planets, or anything at all. The cosmological constant, Lambda. The strong nuclear force coupling constant, alpha sub s. The electromagnetic fine structure constant, alpha. The mass of the electron, m sub e. The mass of the up quark, m sub u. The mass of the down quark, m sub d. Let us examine them one by one. The cosmological constant, lambda. This is the energy density of empty space. The value observed is approximately 10 to the minus 122 in Planck units. The theoretical prediction from quantum field theory is 10 to the power of 120. That is a discrepancy of 10 to the power of 240. The largest mismatch between theory and observation in all of physics. If lambda were slightly larger, the universe would have expanded so fast that no galaxies, no stars, no atoms could have formed. If lambda were slightly smaller, gravity would have overwhelmed expansion, and the universe would have collapsed back into a singularity. The window for a life-permitting universe is vanishingly small. The strong nuclear force. This constant determines whether protons and neutrons can bind together inside atomic nuclei. If it were just 2% stronger, all hydrogen would fuse into helium in the early universe. No hydrogen means no water. No water means no chemistry as we know it. No stars with long lifetimes. No planets. No life. If the strong force were just 2% weaker, no element heavier than hydrogen could form. No carbon, no oxygen, no iron. The periodic table would be a single entry. The universe would be a sea of lonely protons drifting through infinite void. The fine structure constant, alpha, approximately 1 over 137. This dimensionless number governs the strength of electromagnetic interaction. It determines how atoms bind, how light interacts with matter, how chemistry itself operates. If alpha were slightly larger, photons would not reach the surface of stars. Stars would not shine. If alpha were slightly smaller, atoms would be too loosely bound to form molecules. No molecules means no complexity. No complexity means no structure. No structure means nothing that could ever observe the universe. The electron mass, the up quark mass, the down quark mass. These 3 values determine the entire hierarchy of matter. Change the electron mass, and atoms grow or shrink. Change the quark masses, and the neutron becomes heavier than the proton, or lighter. If the neutron were slightly heavier, stars would burn through their fuel in thousands of years instead of billions. If the neutron were slightly lighter, neutrons would decay too fast for atoms to form at all. Is this precision a coincidence? The probability of all 6 constants landing simultaneously within their life-permitting ranges by pure chance is, by any reasonable calculation, effectively 0. This is not a philosophical claim. This is a mathematical statement about the parameter space. The region of parameter space that permits life, any life, not just carbon-based life, is vanishingly small compared to the total space of possible configurations. In 1973, physicist Brandon Carter introduced the Anthropic principle, the idea that the universe must be compatible with the existence of observers, because if it were not, no observers would exist to notice. Robert Dicke had already observed in 1961 that the age of the universe is not random. It is constrained by the time required for stars to produce the carbon essential for observers. How do physicists respond to fine-tuning? Three major frameworks. 1. The multiverse hypothesis. An infinite number of universes, each with different constants. Most are dead. A few by chance permit complexity. We exist in one of the lucky ones. This is a valid hypothesis. It is also, by definition, untestable. It cannot be confirmed or falsified by observation. It lies outside the boundary of empirical science. 2. Deeper physical law. The constants are not arbitrary. They are determined by a unified theory we have not yet discovered. Just as the periodic table revealed that atomic weights were not arbitrary but followed from quantum mechanics, a future theory may show that the constants of the standard model follow from deeper principles. This is the hope of string theory. It remains unproven. 3. The constants truly are the result of chance. The universe simply won the cosmic lottery. This position exists. It is logically consistent. It is also, for many physicists, deeply unsatisfying. Because the odds are not merely long, they are beyond any meaningful comprehension. The fine-tuning problem does not prove any of these answers. It merely states the question with devastating clarity. Why is the universe configured for complexity? Science has no answer, not yet, and any honest physicist will admit it. 3 crises: galaxies that form too early, an expansion rate that refuses to converge, constants too precise to be random. Separately, each one demands an explanation. Together, they point to something larger. The Lambda CDM model cannot explain JWST's galaxies. The Lambda CDM model cannot resolve the Hubble tension. And the Lambda CDM model says nothing about why the constants take their life-permitting values. 3 failures. 1 pattern: the model is not merely incomplete, it is inadequate for the reality it claims to describe. And this is not a reason for despair. Every revolution in physics began with a crisis just like this one. Newtonian mechanics could not explain Mercury's orbit. That crisis led to general relativity. Classical physics could not explain black-body radiation. That crisis led to quantum mechanics. When the model fails, the model must change. And in that change lies the greatest opportunity in the history of physics. Not that the universe is broken, but that our understanding of it is. And every discovery brings us closer to the true nature of existence. If you enjoyed the video content, don't forget to like and subscribe, and let the information come to you. Gravity, mystery, scientific clarity. Exploring the core of reality. Produced by Science Nucleus.